Hi, my name is Sidhartha. I'll be presenting our work titled Adaptive Annealing for Robust Geometric Estimation, co-authored with L. Manam and VM Govindu. M estimation is one class of parameter estimation methods in the presence of outlier data. In M estimation, we minimize the robust cost parameterized by the parameter sigma to solve for the variables theta, as shown in equation 1. Local optimization routines such as the iteratively reweighted least squares are prone to convergence to local minimum. Their graduated non-convexity or GNC is used to mitigate this problem, wherein we minimize a sequence of increasingly harder costs obtained by annealing the parameter sigma of the robust cost. The annealing schedule has been chosen to be a constant traditionally. That is, gamma k, which is the ratio of sigma k plus 1 to sigma k, is chosen to be a constant. We discuss how such a fixed choice of annealing leads to a poor accuracy speed trade-off, and we propose a method to adaptively choose the annealing schedule. Our proposed method helps in achieving the best accuracy in the minimum number of annealing stages. M estimation is used to solve geometric estimation in the presence of outlier data. In M estimation, we minimize the cost function given by 1 to solve for the unknown theta, and the outliers are tackled using a robust loss function rho, which is parameterized by sigma. Local optimization routines such as the iteratively reweighted least squares, IRLS, are prone to convergence to poor local minimum, depending on the initialization. Therefore, GNC is used to alleviate this problem, wherein we start with minimizing the cost for a large sigma naught, which corresponds to a smooth, largely convex, hence easy to minimize cost. And then we successively minimize a sequence of increasingly harder costs till we reach the desired sigma min. The schedule of the solution of the rho of sigma k is used as the initialization for the optimization of rho of sigma k plus 1. The schedule of sigmas chosen for GNC is called the annealing schedule. Traditionally, the annealing schedule has been constant, that is sigma k plus 1 by sigma k, also called as gamma k, is chosen to be a constant. We will discuss the drawbacks of such a fixed annealing scheme. Consider the example of line fitting in the presence of inliers and outliers represented by green and orange circles respectively in the right figure. The non-robust least square solution is shown by the magenta line. Using a large gamma leads to aggressive annealing, wherein we reach the desired sigma min in lesser number of stages, but there is a risk of jumping from one minima basin to another minima basin, resulting in poor accuracy, as shown by the sky blue lines in both the figures. On the other hand, using a small gamma leads to very slow annealing, wherein the number of GNC stages are high, but we can stay in the same basin of the minima throughout the annealing schedule, leading to an accurate solution as evident from the yellow line, which is on the right, which is aligned with the inlier observations. Thus, we desire an annealing schedule which gives us the best accuracy in the minimum number of GNC stages. We propose an adaptive annealing scheme in this work. Starting from the global minimum at sigma is equal to infinity, if we ensure that we stay in the same basin of minimum throughout the annealing until we reach sigma min, then the resulting solution will be a good local minimum, if not the global minimum. Mathematically, it translates to the following. At any given stage k, if we are at the minimum case xk star, we will reduce the sigma to sigma k plus 1 in such a way that the Hessian remains positive definite throughout the interval sigma k to sigma k plus 1. This will ensure that we are in the same locally convex basin of the minimum in the interval sigma k to sigma k plus 1. After we obtain sigma k plus 1, we perform a local optimization to get to the minimum in that basin xk plus 1 star. This process is done iteratively until we reach the desired sigma min. Therefore, given the current solution xk star, we will choose sigma k plus 1 as the least sigma where the minimum eigenvalue lambda min of the Hessian at xk star is positive. Using the principles of calculus, we can derive the Hessian of the robust cost in terms of the Hessian of the least squares cost as in equation 3. We would like to note that the sigma enters the Hessian only through the terms Li and Mi. Also, we would like to note that the computational time of finding the lambda min depends only on the dimension of the Hessian or the number of variables in the optimization. Practically, we observe that lambda min of xk star of sigma is an increasing function of sigma in most part of the sigma space. Therefore, we can perform binary search in sigma space to check where the Hessian is just about to lose its positive definiteness. This means that at every value of sigma, we have to evaluate the Hessian matrix and calculate its minimum eigenvalue. This is prohibitively expensive, especially when the number of observations is high. But this can be made efficient by looking at the expression of the Hessian and the fact that the sigma enters the Hessian expression only through the terms Li and Mi. Therefore, we propose to do a piecewise polynomial approximation to Li and Mi, which will ensure that h of sigma is equal to c by sigma square plus d, where c and d are piecewise constant matrices in the piecewise intervals chosen for Li and Mi. This ensures that during the search in sigma space, we need not calculate Li and Mi's for all the observations for calculating the Hessian. On an average, this leads to only a few computations of the matrices C and D during the entire binary search, thus making the computation of the sigma k plus 1 much cheaper. We illustrate our adaptive GNC approach on the problem of pairwise 3D registration. The problem is, given the correspondences AIs and BIs between two 3D scans, we need to estimate the transformation R and T that aligns the two scans. The M estimation problem for the same can be seen in equation 5. Note that in general, at sigma equal to infinity, the robust loss rho is nothing but the traditional least squares cost, for which many problems have certifiably global solutions. In this particular case also, due to Umayama, we have a global minimum for the least squares solution, and the IRLS subproblems, which are also weighted least squares problems, they also admit as closed form solution for the global minimum. We perform the experiments on the synthetic data sets for different noise levels, small and large, for different number of observations, and for different outlier fractions ranging from 0 to 50%. We observe that our method outperforms the other state-of-the-art methods in the mean rotation errors and the translation errors while being efficient. We also test our method on the ModelNet dataset, and we can see that our method achieves the least mean rotation and translation errors while being reasonably efficient. We perform experiments on the real-world datasets, namely 3D match and the Kitty datasets. We can see that our method achieves the most number of successful registrations while giving smaller mean and translation errors. We can see that our method is extremely efficient compared to the other state-of-the-art methods. This is one example of registration of two point clouds with low overlap. We see our method is able to align the best with respect to the ground truth compared to the other methods. We also do a comparison of the fixed annealing where gamma is constant. For the small gamma, we pick gamma equal to 1.4, and for the large gamma, we pick gamma equal to 2. We observe that our method combines the benefits of both small gamma annealing and the large gamma annealing by giving the best accuracy in the least number of GNC stages. In conclusion, we saw how annealing mitigates the problems caused by IRLS and helps in converging to a good local minimum, if not the global minimum. Also, we saw how fixed factor annealing can result in a poor speed accuracy trade-off. We proposed an adaptive annealing approach based on tracking the positive definiteness of the Hessian of the cost function. We also demonstrated our method on the 3D registration problem and showed superior results compared to the state of the art. We note that the first two authors are supported by the Prime Minister's Research Fellowship, Government of India, and this research work was supported partly by the Department of Science and Technology, Government of India. Thank you.